The Born-Haber cycle is just another version of Hess's law. It's just specific to making ionic compounds. And it's the series of steps, which are a bunch of reactions that we're going to use to represent the formation of 1 mole of an ionic compound from its constituent elements. So in this video, I'm going to do 3 things. I'm going to have us focus on the formation of calcium chloride, which would mean I got calcium, metallic calcium, and alkaline earth metal, with chlorine gas, which is a halogen, and diatomic, and it's going to form calcium chloride, an ionic compound made of calcium ions, which are 2+, chloride ions, which are 1-, so we're going to need 2 chloride ions to balance the 2+ charge of the calcium, and then ionic compounds at room temperature would be solid. Keep in mind that this is a formation equation. We want 1 mole, and it just worked out nicely with this one. Also keep in mind this is a molecule with a covalent bond, a single bond, just to be specific. And this is an ionic compound made of ions, this cation, and these are the anions. Okay? In the back of the book, you can find the enthalpy of formation for this, and it's -745. So you might be saying, well, we're done, right? But we're not. What we're going to learn about in this video is the Hess's Law version, so the steps. I'm going to go through it like Hess's Law and learn the steps that it takes to make a calcium chloride ionic compound, 1 mole of it form. The other thing I'm going to do is I'm going to draw what's called the Born-Haber Energy pathway, or the energy diagram, okay? And I'm also going to draw some particulate views. So this is going to be a pretty hefty video. It's going to include a lot of things, hopefully all wrapped into one, and make it easy for you to comprehend. Okay, so here we go. So if I'm going to make calcium chloride, you might say, well, some of the steps are going to be calcium turning into an ion, so you might have ionization energy, and you might have electron affinity because chlorine should turn into an anion and make chloride, so you might have that energy. So yay, it's just 2 steps, but in the end, it's not. So it's actually a series of 5 steps. So I'm just going to list the steps with just symbols first, and then I'm going to go over Hess's Law with all the reactions, and then I'm going to draw it with the energetic pathway, or the energy diagram, and I'm also going to draw particulate views. So it's going to be fantastic. Here we go. So the enthalpy of the first step is called the enthalpy of sublimation. So any reactant that is not in a gaseous form has to be. So in this case, we're going to have calcium turned into a gas before this, this ionic bond can form. Next, the enthalpy of bond energy. So I'm just going to do some, shorthand, and I'll write it out thoroughly in a second, but that's bond energy. So anytime we have a covalent bond in our reactants, we must break that bond to make them atoms again. The next step is usually the one people predict, which is that you have ionization energy, the energy required to make those cations, and you could have a first, a second, a third. So it just depends on what metal you're dealing with and how many electrons it has as valence. Great periodicity review in this chapter. And then you have, or this section, you've got another step, which is the electron affinity. Another step you probably would predict, which is step 4, that the anion has to form. So we have to make chlorides, and so that would be, something you'd predict. And then the most important step, really, to make the energy make sense is this lattice energy step. And it's the energy that will be, in this case, released when we have our ions finally formed after step 4. And then with Coulombic attractions, or some people say electrostatic attractions, they will bond and release a lot of lattice energy in the process. Because again, we're making the compound, we're not taking it apart. Okay, so let's move on to why this is Hess's Law. So this is our goal equation up here, this one right here. So what are the steps that make that happen? So I'm going to write it more detailed now. So the calcium solid, and I'm going to take my time here because there are a lot of easy places to make mistakes. In fact, I think this might be my 2nd or 3rd try or more of this video. So calcium solid turns into calcium as a gas. I'm going to go kind of slow, and you do the same. And that is the sublimation energy. And it's a value that you would have to look up, or somebody would have to tell you, or maybe it would just be given. So I looked it up, and it was 178 kilojoules that had to be added for calcium to go from a solid to a gas. The second one is we also have to have all of our reactants turned into atoms. So we have to break this, in this case, single bond, because chlorine would make a single bond as a molecule. So it's going to be 2 chlorine. Now, not an ion. In fact, you might want to add a 0. It is still gaseous, but it's chlorine atoms. So this, you probably would easily find this one because most textbooks have bond energy tables whenever you learn about dot structures in Vesper. So this would be plus 242 kilojoules. So that one might be a little easier number to find in a textbook. All right, step 3, I'm going to show this in many steps though. Step 3 is the ionization energy. Now, because we have calcium now in the gaseous form, we want to have it become an ion, in this case a cation. But I'm going to do this in a stepwise formation. So we have our first electron come off, and then this same calcium ion, 1 plus in the gaseous form, turn into calcium 2 plus. And then it wouldn't do this again because the energy to remove a third electron is very high. Calcium also has 2 valence. So there's a couple ways you can answer this. And then these would be the first ionization energy. And then don't be surprised if some books actually use an S instead of a Z. That's the same thing, okay? Don't worry. And then there would be a second ionization energy. This is also where you could break off into a really good periodic table review on, why is the second one always larger and why is it kind of a fair amount larger? So if you looked up in a book, I bet you'd find this one. The first electron to be removed is 590 kilojoules. And then the second one is 1,145 kilojoules. And those are the 2 ionization energies. So together they add up to, I have it in my notes here, is 1,735. So if you want to put that, you could add them together. Now what I'm going to do is after I just worked so hard to write these, I'm actually going to put them together and then I'm going to use this one that I'm writing right now for the Hess's Law because I think it'd just be less confusing. So what I'm going to do is make sure, and actually, before I even erase these, you really should have that these are gaseous. It's really easy to forget states of matter, but they do matter here. And then I'm actually, after I worked so hard, I'm going to get rid of these now. But I did want you to see those 2 separate steps because they do happen in 2 steps. All right, say goodbye to those. And I'm just going to move this one up in that place. So really now I made it look like it happens in 1 step. Okay, now moving on to step 4, I'm going to try to again make sure I don't make any mistakes here. So we're going to take and we want our 2 chlorine atoms that are gaseous to gain an electron each, so both electrons 2 total, so that they both become, or 2 moles of it, you could say 2 moles of it become chloride ions in the gaseous form, okay? So that is our enthalpy of electron affinity. Great. And then be careful, it's negative 346, and I bet you could find this one in your book because there's some interesting discussions about electron affinity with the halogens. But you'll have to multiply it by 2 because remember we gained 2 electrons, so that's per 1. And it doesn't have a different value for electron affinity, that's just the way it is, okay? Trying to make a good look at my, my steps here, make sure I don't have any mistakes. All right, now what can happen, I see this often, they might want you to predict the 5th step. They may even say, I want you to predict the energy of this lattice energy step, like the quantitative value. So I'm going to leave that for just a second. I'm going to do that last. And I'm going to put this goal equation, I'm actually just going to take it and steal it from up here. So I don't need, hopefully this is faster than rewriting it. So that's my goal, okay? And what I want to have happen is when I do Hess's Law, and I haven't written the last step yet, I want everything that's, not in this goal equation to be removed. So let's write out our last step, and it's that our calcium ions that are in the gaseous form are 2 chloride, and again, you could say 1 mole and 2 moles, but I'm just saying, 1 and 2 is fine. And then it makes calcium chloride, but it would be 1 mole of calcium chloride, solid. Okay, and I did this, I made a mistake again. There we go. Sorry about that. Make sure you fix this. I think because I'm so used to chlorine always being aqueous, this is a gas, so please fix that. Okay, so let me just check I got all my states of matter right. So solid to gas, 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 we're just breaking the bond. I'm going to do my review just for myself. Got calcium turning into an ion, releasing electrons. Those chlorine atoms gaining the electrons, turning into 2 chlorine ions in the gaseous form, calcium gaseous ions, 2 chloride gaseous ions, making your calcium chloride solid. Boom. Okay, now it's time to predict this enthalpy, or you can calculate it. So if you take all of these and add them up and then figure out what the missing part is, you would find that it is negative 2,258, a very large value, which makes sense because if you think about it, for the longest time, this was very endothermic. We got a little bit of exothermicity here, but there's where the exothermic reaction takes place that really helps us get this negative 745. Okay, let's do the Hess's Law and let's move on to drawing the graph or the energy pathway diagram and then the particulate views besides. Here we go. So let's switch to get rid of these, okay? Let's do some red. So we have calcium gas, so we need to find that that's produced and then it's consumed kind of here, okay? Because again, for Hess's Law, we only want what's left in the goal equation. So down here, these are the only things that should be left inside of this area. Here we go. 2 chlorine atoms in their gaseous form that are going to be canceled here. And then we have the calcium gaseous ion here. We have 2 chloride ions here and here. And then electrons also have to cancel. You'll see that when you do redox chemistry, maybe later on. So again, we have sublimation, bond energy, ionization energy, 1 and 2, electron affinity, lattice energy. When you put it all together, you get your calcium, chlorine, and then it does form your calcium chloride. If you check these and add it up, you will get that value. Okay, so there's your Hess's Law portion. Now let's move on to the energy pathway or the energy graph, okay? So what I'm going to do is I'm going to have you, if you have a brand new sheet of paper, get a brand new full sheet and keep it portrait, meaning up and down. I'm going to barely be able to squeak everything on here and get to fit. So you might want to make sure you have a brand new sheet of paper. On the axes here, you're going to say I have enthalpy, okay? Then what you're going to want to do is have what I call a 0 point. This is where you have 0 for an enthalpy, and that's going to happen when you have everything in their standard states, which is our calcium solid and our diatomic chlorine gas. Great, okay? Then what will happen next is usually you'll see, or if you have to draw this, a kind of a bold arrow that this is that enthalpy of formation. This is when it reaches sort of that more stable crystal lattice structure that an ionic compound forms. And then this again, I'll put the numbers in here. This is at 745 because that might help you kind of correlate the steps. You might even want to write more than even I'm writing. And then that's forming that calcium chloride solid. That's the crystal lattice, okay? Didn't know why my L looked like that. There we go. Don't do a capital L, it's lowercase, okay? All right, so then what I'm going to do is above these, I'm going to draw the particulate view of what it looks like at this point. So what I'm going to do is draw just 4. I just thought 4 was a good number. It could be more or less, but we just have to keep it proportional. So I'm going to say that for calcium, and I'm not drawing that this is also not going to be like the right amount for each. There could be a limiting and excess here. I'm just going to draw 4 of each just because I think we need at least a few to look at. So I'm just going to draw 4 calcium. Now really you draw a lot more because you want to show that this is in a metallic lattice structure like this, okay? And they're close together and they are a solid form. Your chlorine is a diatomic gas. You want to kind of draw them kind of small and then just kind of show that there's I'm just going to draw again 4 total. Now, realistically, it's 1 calcium for every, 2 chlorides. So I'm not drawing these particulate views to be like per the stoichiometry. Just sticking with 4, okay? Keep something simple. All right, next. What's going to happen is I have to go up this pathway and I have to do step 1. And step 1 was the sublimation step. So you might want to write down more than I am, but I'm just going to say this is step 1. And it was the energy that had to get put in, and it was plus 178 kilojoules to have your calcium turn into gaseous calcium, and your chlorine gas is already gaseous, so that just stays the same. So what I like about the particulate views is let's draw what that would look like. And again, this is why I'm using 4 of each. Again, one more little disclaimer. I'm not trying to show you the proportionality of this reaction. I'm just sticking with 4. So nothing happened here. There's 4 total, atoms, but they're bonded, so there's 2 molecules, okay? And then in here, I'm just going to draw the calcium, but now I'm going to show that they're much farther apart, okay? If you really wanted this to be proportional, you could do this. But I think then, and maybe I will, just because it'll be a lot less to draw. So that means like when I started, I only want to draw 2, okay? So if that helps you and it makes more sense, just pretend that you drew, all those crystal lattice, atoms. But let's just stick with 2, okay? Because then it does sort of match the proportionality of the reaction. Okay. Next, So that's that step. So the next one is going to be step 2. So that's step 1 was sublimation. Step 2 is the bond energy. And then that was plus 242. So that was breaking the chlorine diatomic single bond. So we'll kind of put another plateau, kind of like stages of how this happened. So again, the calcium, that is a gas, checking my states of matter here, and then my chlorine are now 2 chlorine atoms that are gaseous. I'm going to put a little 0, just so you know these are not the ions yet. So in this picture right here, I'm just going to draw above what happened. And we'll just say nothing happened with the calcium, these are still gaseous, farther apart at least as possible. And then we had these turn into atoms. So then I'd have 4 of them. I don't know why I drew 5. We'll get rid of that one, okay? So I have 4 of them. So the bond has been broken. So now they're free mobile atoms. Okay, next step. Now I'm going to actually have to increase this graph, okay? So here we go. So this gets even larger. That's why I said having that big full sheet would be great for you guys. Okay, let's go way up to there. Okay, because this next pathway, you have to do the first ionization energy and then you do the second ionization energy. So you kind of want to show that this is a pretty hefty increase. And this is the only one I'll do these with. So this step 3 is, that was 1,000 total. What was that? What did I say? 1,735. I'll just put it right here, 1,735. So that you want to kind of show proportionally, as best as you can, the amount of energy that had to go in for that step. So then at the top of here, this is where you reach kind of the energetic top of this whole thing. And then we're going to start coming back down. So when this hits the top of here, I'm just going to bold this line. And sometimes this is really bolded in your books too. This is the top. This is where we have our calcium ions in the gaseous form. We have our 2 chlorine atoms, but they're not ions yet, okay? And then what happened is, let me just show you kind of in stages here. So I'm going to do 3 kind of pictures for the calcium, but there's really only this last picture that I'm going to have above it that is the most important one. So keep in mind that your calcium was maybe this big, but the protons are going to stay the same, but it's going to lose an electron. So what will happen first is it'll shrink down to a smaller size because of the fact that there's less electron repulsion. So you have calcium, neutral. This is calcium with a plus. Then it actually sheds an entire electron valence shell besides, but the protons stay the same. There's 2 less electrons and 1 less energy level. So there you go. So now you're shrunk way down. So you want to make sure that your calcium ions that are 2+, these right here, okay, that they are much smaller than the calcium atoms they came from. And then what happened with the chlorine? Nothing. Okay, not yet. It's getting its turn next. So 1, 2, 3, 4. There we go. Okay, chlorine, you're on deck. So now it's your turn, per se, to then have those electrons that were released. And if you want to put the electrons in here, you could put them like right here. You could do either one. Some books put the electrons in and others don't. So if you wanted to, you can put them here if you felt like that made more sense. But then we kind of have to put them in the next one here. So when we go down this next path, let's just say we go to here. It's a really hard time. I have to zoom in. This would be our step 4. I never even said this was step 3. Check if I have any other mistakes. So then at the end of this, I'll check one more time and I'll repeat it all just to make sure I don't have any more errors here. This is the last time I'm making this video. 3rd time's the charm, we'll say. So then you have your calcium ions. Nothing happened with those. But your 2 chloride have gained the electrons. So maybe if you want to leave it, and that's why I said, like, a lot of people don't put the electrons in there, they just assume. So if it kind of bothers you, then just get rid of them, okay? But they are important in this process, obviously. So the next thing you want to do is maybe put the number down. So that helps you. Remember, this was the 2, actually, let me put it underneath here. It's a little messy, but 2 times the negative 346. Because remember, it was 2 electrons that had to be added. And the chlorine releases 346 per each chlorine per mole. Okay, pictures. Picture time here. There we go. And then what you want to do is show what happened to chlorine. So I'm going to first do the calcium because nothing happened between the last 2 steps. So it's still kind of like, oops, I knew I'd change the color. So there and then there. Okay, so you want to make sure you have it as a little smaller size. So if I were to zoom back out, you know, it should look smaller than it did as an atom. And then think about what's going to happen to that chlorine. Proton count is going to stay the same. One more electron, you have more and more electron repulsions. So what's going to happen is the size of the chloride ion is going to be larger. So let's just draw 4, okay? Because technically if I had 4, we'll say we gained. Now that doesn't match the reaction, but that's okay. We have like a double batch, we'll say. Okay? Particulate views, you have to draw at least more than one. It's kind of hard to just draw one. Okay, last but not least, this is the big lattice energy step here. So as we go from here to here, I'll draw it way on the outside and try to keep it as straight as possible. This is our step 5. And then this was that negative 2258 kilojoules. That was the lattice energy forming, or the lattice energy of the ions forming together into a ionic compound. Okay. All right, so let's draw what that looks like, and then I'm just going to quickly review and make sure I don't have any other mistakes in here. If I have any, I'll try to fix them. So let's say we have 2 chlorides, then we would say, you know, 1 calcium would be bonded to it. So you want to try to draw at least a little mini lattice structure here. I'm not worrying about a unit cell. Those of you that know what that is, I'm not doing that. Let's just say that it's making a repeating unit of crystalline structure, okay? So, you know, in most books, again, they'll try to show you that this looks like a solid cube. Not the best cube either, but I'm going to move on. Terrible cube. Okay, so let's just check these steps one more time, make sure I don't have any mistakes as we go. So we got our calcium solid, chlorine gas. Got your first pictures. We got to make them into all gases, so that's going to separate those solid, you know, atoms from each other. There's your energy. You've got to then take your covalent bond and break it, so you have your chlorine atoms released, and then nothing happened here. You have to have the electrons come off of the calcium, which was a very energetic step and all endothermic all the way up to this point. There's your calcium ions, and again, if this bothers you, you know, really these were just the other ions, you know, but predecessors here, the atom and then the 1+ ion. So you got your calcium 2+ ion, you've got your chlorine atoms, they're all in the gaseous form. And then, I did forget a state of matter. So then what you have is you have your, you have your calcium 2+ gaseous ion. I just added right here that we have our chloride gaseous ions. So calcium ions, they're cations, chloride ions, which are gaseous. It's really late making this video. And then there's 2 to 1. Then you have electrostatic attractions, Coulombic force, and you get this huge lattice energy to make your beautiful crystal lattice that looks probably better than my picture. All right, chemists, I hope this video helped you. I know it had a lot in there, but again, the whole point was to, you know, show how the Haber cycle is nothing more than a Hess's law for ionic compounds. You have 5 steps involved. You can prove Hess's law from it, maybe even find a missing lattice energy. Then this would be what's called the energetic pathway for that. I can zoom back out a little bit so you can see it all at once. And it's, you know, adding all these steps together, come back around, you get a few, you know, exothermic parts here and then a large exothermic lattice energy here. And overall, the overall enthalpy of formation is 745. All right, I hope you like this video. Like, subscribe, comment. I have other videos on thermochemistry, and good luck, chemists. And I, you know, wish you the best. And come back and learn chemistry from me if it was helpful. All right. See you later, I hope, and good luck.